Welcome to Dr. Jed's continuing series on calculus. Today's lesson is section 3.8 from Rogowski, the inverse function theorem. We don't actually use the inverse function theorem very much, except to find formulas for things that we need. So the first thing we're going to do though is state the theorem, talk about the theorem, kind of give a hand wave proof, a little bit of a proof, not really very much, but just sort of enough to see how it works. Use it to derive the derivative for inverse sine, and then while we're at it, look at all of the inverse trig functions, find their formulas, and then do a few examples. So first, the formula, or actually the theorem, excuse me. Suppose we have a differentiable function f. Now, differentiable means it has a derivative. That's a fancy word for saying if f has a derivative, and if f has an inverse, we want to know what the derivative of the inverse is. Let x be in the, now I'm emphasizing here, it's in the domain of f inverse. F inverse is not 1 over f, right? It's the inverse, the opposite. So instead of x cubing, it's the cube root. Instead of sine, it's the inverse sine. So how do you find the derivative of that? The derivative of the inverse function is 1 over the derivative of the original function, f, at the inverse. Notice this looks a lot like the chain rule, except it's missing the extra piece. And that's how we're going to prove it. So let's take a look at the proof. So suppose we start with x is equal to f of the inverse of f at x. That's true. That's always going to be true. Why? Because if f is an inverse, this is one of the properties of inverses. Now, we're going to take the derivative of both sides. The derivative of x is 1. And by the chain rule, the derivative of f inverse will be f prime at f inverse times the derivative of the inside, which is f inverse here. So then we just divide by that, and we get our theorem. Now, I call this a proof in quotations because there are several things. I assumed the inverse has a derivative. I also, without real justification, took a derivative of both sides. I've done that before, but I want to make sure you understand that we need to justify that if we were going to make a formal proof. But it works, and it's right. So let's do an example of it. Finding the derivative of the inverse sine of x. Well, that's the inverse function, that's the f inverse. So our original function is the sine of x, and we're going to need its derivative. And the derivative of the sine is the cosine. So according to the inverse function theorem, the derivative of this will be 1 over the derivative of f at f inverse. Now, this is trigonometry, so we can figure it out, but that's the derivative. However, it's not at all simplified, so we should simplify that. Let's take a look using triangles. The inverse sine of x, what is that? Well, the sine of something takes an angle and produces, by the way, that's supposed to be a right angle, a right angle, a right triangle. The sine takes an angle and produces a value. In triangle terms, it's the opposite over the hypotenuse. The inverse triangle takes the opposite over hypotenuse and produces the angle. So suppose this is the angle in question. The inverse sine of x says, well, the sine of this is x. Or if you like it better, x over 1, because dividing by 1 doesn't do anything. And if you recall, the sine is the opposite over hypotenuse. Opposite over hypotenuse is going to be x over 1. So opposite hypotenuse. Now we want the cosine of that angle. The cosine is the adjacent over the hypotenuse, so we need to figure out what this is. This is a right triangle, so Pythagorean theorem applies. A squared plus b squared equals c squared. So just do a solving of that and you get the square root of 1 minus x squared. So it's adjacent over hypotenuse, and that's the cosine. So the bottom is just going to be square root of 1 minus x squared over 1. And that's on the bottom, so we end up with 1 over square root of 1 minus x squared. You can do this with all of the trig functions, although some of them are messier. But let's take a look. Here they are. Notice the sine, that is the one we have. The cosine has a minus in there, and that happens because the derivative of the cosine is the minus sign. So there's where the minus comes from. The tangent, the reason this happens is the tangent's derivative is secant squared. And there's a relationship between secant squared and 1 plus tangent squared. That's where this comes from. Those ones over there are messier. And frankly, they're not used very much. These are the three big ones. They're on your calculator. Those three are messier and people don't use them, but they're the formulas. And notice there are still patterns. The secant, the cosecant, one of them has a plus, one is a minus. The cotangent and the tangent, one is plus, one is minus. The sine and the cosine, one is plus, one is minus. There's a lot of relationships here, and you could spend weeks studying interrelationships rather than 10 minutes or so. All we're going to do is right now and use them. So let's do an example. Find the derivative of x times the inverse secant of x. And I said we never do this, but well, here we are doing it. So this is a product. So the derivative of this will be the derivative of the first thing times the second thing plus the derivative of the second thing times the first thing. Let me rewrite that to be a little prettier, but we're not going to get very far. That's as far as we can go. Notice this x and this absolute value of x. This works when x is positive, because they cancel, or when x is negative, because that creates a minus, and otherwise it cancels. These two pieces are not going to combine in any way, and they're just done. So let's do one more example, and then we'll be done for today. Here is the graph of y equals the inverse cosine of 4x. That's the curve. And I've drawn a tangent line when x is 0, and I want to know what that line is. So recall, for tangent lines, we find the derivative first. So this is a chain rule. The inside is 4x. So it's the derivative of the cosine, the derivative of the inverse cosine, add 4x, times the derivative of 4x. So using our formula, it's minus 1 over, well, normally we would have a, I'm going to write it, but it's wrong. 1 minus x squared. But that's the thing that goes inside, right? Instead of x, we want our inside, g of x, to be here. That's what the chain rule says. So this is not an x, it's the thing inside. Thing inside is 4x. So I write 4x squared. But that's still not right, because it's really the 4x that gets squared. It's not 4 times x squared. This is right. Except, of course, we still need one more piece. We need the derivative of the inside, which is 4. Now, all of that work down here, for our purposes, is not that important. Why? Because we want this when x is 0. When x is 0, we want this value. That's its slope. So the slope is just plug 0 in for x. If I plug in 0 here, I get 0 squared, which is still 0. 1 minus 0 is 1. Square root of 1 is 1. So I have 4 times 1, 4 times minus 1. We're almost done. We just need to finish off. We have y equals minus 4x plus something. And if you look at this graph, you can see it should be pi over 2. How do we know it is? Because actually, when x is 0, what's the y? So plug it in here. When x is 0, we have the inverse cosine of 0. In other words, what angle gives us a cosine of the angle equals 0? And the answer there is pi over 2, because the cosine of pi over 2 is 0. Since 0 times the minus 4 is still 0, what we need right here is pi over 2. There's the line. That's what it looks like. The slope is going down. It doesn't look like it's a slope of 4, but that may be just because we drew it kind of funny. It's a sketch rather than a perfect drawing. If you draw it more carefully, you may see the slope is in fact minus 4. But there you have it. Applications of the inverse trigonometry and their derivatives, and that's it for this time.